So let's continue with our book. Just now we're on page 7, so we are continuing at a very slow glacial pace, but that doesn't matter too much. Sometimes whenever you're going through a book, you can go through very slowly and then it speeds up and it slows down. But now today what we're going to do is recreate these images. So you'll see these images on page 7. So we'll go ahead and we'll do this now. So we have the function that we want to approximate here in green. And this is our sine 2 pi x. And then we have the function plus the noise, which are these green circles. So this is our training data. And we're going to approximate it by a polynomial. And we're going to set it out, first of all, with only one weight. That is W0. And W0 is just going to give us a single line. And you can see this single line in pink. And this is the same as we see in the book on page 7 in the top left hand corner. So you'll have access to this and all of the rest of these simulations if you click on underneath this video. Now we have the two parameters, W0 and W1. And it gives the approximating line you see here in pink. And this is similar to the diagram you see in the book where it says m is equal to 1. So again, we have the original function we want to approximate in green. So this is our sine 2 pi x. We have the original function plus the noise, which are these green dots. So this is our training data. And then we have the approximating function, which is our polynomial in pink. Now we have generated this polynomial using 4 of our parameters. We've used W0, W1, W2 and W3. So the approximation has gone up to W3 x to the power of 3. And this is similar to the graph we see in the book on page 7, where it has m is equal to 3. And finally, we have the polynomial approximation in pink here. And this is using 10 of our parameters. So we go from W0 all the way up to W9. And this is similar to the graph that you'll see in page 7 that says m is equal to 9. Now, there is one difference, and that is in page 7, you'll note that the approximating polynomial goes through all of the green dots exactly. That is, it's an exact approximation for those particular points. Now, in this instance, our values don't go through these points exactly, but they're relatively close. And the pink curve here follows very precisely with the curve you see in the book. Now the reason our curve doesn't go through all of these points is that the values that we've used here for our weights, W0 all the way up to W9, are the values which are in page 8 of the book, table 1.1. So these are the parameters that I have chosen in order to generate the simulations, and they come from the table on page 8 of the book. So we started off with only the W0 weight, and it was 0.19, and then we went on to the next simulation where we had W0 and W1, and then the next simulation we had 0, 1, 2 and 3, and in the final simulation we went from 0 up to W9. Now these values here have been generated using the training data which the author has for his simulations. But the training data that we have is going to be slightly different, because the values that we have for the training data are going to be normally distributed in a random fashion. So it means that our training data is not exactly the same as the training data for the author in his example. So what we really need to be able to do is to generate the weights W0 all the way up to W9 that fit within our training data. And we don't have a method of doing that just yet, but we will get to that as we work over the rest of the book. Now, one thing to note here is that we have an issue, and the issue is that if we were to increase the number of weights, in this instance we've increased them to a number 9, then we actually get something called overfitting. So ideally we want this pink curve here to hug very closely to the green curve. Now it does match the green curve very closely at the green dots, but if we were to go to a point not at the green dots, then you can see that the approximation goes wildly astray. So for example, if we pick a point over here, you can see that the approximation is going to be away down here, which is a very, very poor approximation. So in this instance, this is called overfitting, and it's something we would like to avoid. So the value for our parameters W0, W1, W2, we called this parameter M. And what we would like to be able to do is choose M so that we have the best fit. So this process of choosing this value for the order of our polynomial is called model comparison or model selection. And we need to get a process whereby we can define the best fit in terms of this value M. In the next video, we will look at how we can choose the value of M in order to avoid this overfitting. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.